Welcome back, my structural analysis friends. In today's lesson, we're going to be talking about snow loads and how we determine the factors and the computations necessary by structural engineers. We'll be looking at things like heated buildings and unheated buildings and the effect of roof slopes on snow load values and all of the basics that go into performing these basic calculations. So without further ado, let's get started. So much like what we did with the wind loads in the previous videos, in this video we're going to be discussing the basic factors that will affect snow load. Now again, remember that a lot of this is an environmental effect, so this will also be utilizing the information we talked about in the environmental load factors video a couple videos back. So if you need to review that, please by all means step back and rewatch that one if you need to. For us though, we're going to try to kind of assume that we've got that under our belt, and we'll go from there. All right. So for us, snow loads are caused by deposited snowfall on exposed areas of a supported structure. That's the technical definition of what a snow load is, according to ASCE 710. Now, the provisions that we're going to be looking at are all located in Chapter 7, and we'll talk about, things like, decks and roofs and pitches and thermal factors and all sorts of other things that we'll start to kind of look at, and we'll kind of walk our way through some of those factors. So what I've done is I've broken down the basic factors for snow load into a list of 5 different categories. Okay, the first one is the geographic location. Where in the world are you? Strongly affects the snow, right? If you're in southern Florida, you probably don't have much snow, but if you're in the Upper Peninsula or Alaska, you have some pretty severe snow effects. So for different parts of the country, this will be differently. So there will be maps involved again. Much like what we had with the wind, there are snow maps that we'll be looking for. And those will define what we call the ground snow load parameter, or PG, and you'll see that. Okay. The next factor we have is exposure. So much like the wind, snow is affected by wind. So if you're in an area that has a lot of wind that could blow the snow off the roof of your structure or keep it from landing on your structure in the first place, that becomes an issue. Okay, we're looking for the ability for snow to settle onto a building before it gets interrupted or moved away. Okay, and so we'll have an exposure factor that will play a role. Okay, and that's also a function of the immediate surroundings around you. Again, kind of like what we talked about with the wind in a couple of videos ago. All right, there are thermal factors. Is your building heated or unheated? That will play a role. Okay, the importance factor. That's again that environmental factor that's related to the risk category of the building, and then of course the slope of the roof will be a correction that we'll have to make. Okay, now snow is often greatly affected by the presence of wind, which results in redistribution of snow location on a structure. Okay, that when the wind moves snow around, we get an effect known as drifting. Okay, now in this category, in this class, we're not going to focus a whole lot on drifting phenomenon. Okay, we'll add a video for that later. We're going to basically be calculating what we call the flat roof snow load, or the non-drifted snow load, just to kind of get a sense of how all these factors work. But at a later time, we'll add in a drifting video for sure. Okay. All right, so let's start with the first category. All right, and that is the geographic location. Okay, so what I've done, kind of like with the other packets, is I've pulled out excerpts from the ASCE 7 so you can see how they're starting to define these kind of things. All right, so the geographic location determines our ground snow load value, or this PG, this P ground, okay, which is based on the location of the structure. All right, so PG comes from maps again. Okay, so that's the western U.S. Let's go take a look at kind of the eastern U.S. and kind of show some things for our particular snow values. Now, it's kind of hard to visualize down in here, but like here's Illinois, Florida, so forth and so on. Okay, and if you zoom in, and again, those of you that have access to this map in a print form or something, you'll see that through most of the Midwest, central U.S., we're looking at a ground snow load value of about 20 PSF. Okay, and then this band goes to 15, this one goes to 10, this one goes to 5, and then if you get down into here, it's basically a zero snow load value. Okay, they don't expect to get snow obviously down in Florida. That's why people move to Florida. Okay, now as you go up, it goes up, and each of these contours represents 5 pounds per square foot. So if this was 20, there's 25, 30, 35, 40, you know, and so forth and so on. I think this goes to 50, this goes to 60, and then way up northern Minnesota, you get into 70 pounds per square foot numbers that can start to happen. Okay, all right, now you can see that it gets even higher in specialized regions as well. Okay, and you'll see like we can get all the way up to 100 pounds a square foot, way up, you know, on the UP point of this, some very big snow loads can start to happen, and we can even get up to looks like 50 or 60 up into New England. Okay, now I will point out, you know, a couple, and again, it's kind of hard to see on this video, but I will point out some special regions that exist on these maps. Right here, you'll see a variable that calls CS. Okay, there are a couple of them, and you'll notice that they're almost always around a body of water or something like this. And what these are, if you've ever driven, say, from Cleveland, Ohio up to Buffalo, New York in the winter, you'll know exactly what this is. Okay, these are what we call the lake effects. Okay, they're basically specialized regions of snow that don't meet the kind of the standard normal that we can measure. Okay, and so you have to rely on local meteorologies and requirements in order to be able to calculate those values. But you know, you can get lake effects coming off of Lake Erie, over coming into this region, or Lake Michigan over here, that are measured in feet. You know, it can be 4 or 5 feet tall of lake effect. It's a fine powder dust that, as the wind comes across the lakes, it evaporates and then freezes it instantly into this microfine dust. That can be quite substantial, and so these are special categories. So whenever you're looking at these maps, you got to be very careful on these CSs. You also get into a bunch of CSs kind of down through here, okay? And this is the Appalachian Mountains. You're getting into West Virginia, and southern Pennsylvania, western North Carolina, those kind of areas, and those will be special as well because the environment's a different, non-normal situation. So always be careful of the CSs. If you get a CS, if you're working in an area that has a CS, snow ground snow load, then you need to be talking to local authorities to find out, what their design parameters should be historically. It can be substantial. It can be much more than even the hundreds in some cases. So that's why that's called out on the maps. The ASCE 710 basically punts on numbers in those specialized regions. But for the rest of us that are kind of out in the Midwest and stuff like that, it's pretty easy to use these values, and this method will work very well for those. Okay, so that's the eastern U.S. If you go look at the western U.S., I have that map here too, just to kind of highlight. You can see that it gets all kinds of crazy. You get some very high pockets that happen here, and again, a lot of these are kind of specialty regions as well. If you look out into here, the entire state of Colorado is almost a CS. I guess there are some smaller values. It gets to 20 in the lowlands, but you get out past the Continental Divide out into Denver, and it's a specialized snow case. And again, that's why people go to ski there, is because the snow is deep and very intense. But you can see that there are pockets all over the place. So again, it's a matter of just figuring out where you are on the map and being able to design for the snow accordingly. All right. So that's the maps. That's PG. That's our first item. Okay, all right, so we've talked about the CS, we talked about the maps, okay, lake effects, we've talked about those. Okay, now we're talking about our exposure. Now again, we talked about this in our environmental factors, okay? We have, a little bit, but the exposure for snow is a little bit different, okay? It uses the same exposure classifications as BCD, okay, but then they start defining what we call a specific exposure for the roof, okay, and you'll find this in table 7-2, okay, and they define that as kind of an A, B, or C exposure, okay, and A exposure is fully exposed, meaning it's kind of out in the middle of a big open field, there is no shelter, no trees, no buildings around it, that when the wind comes through, it can very quickly blow the snow off of the roof and reduce your loads, okay, versus, a partially exposed, which is basically it's neither A nor C, and C is the sheltered, okay? And this one occurs, the image that we like to use is that there's my building, and I have a whole bunch of trees, kind of up in the woods, your cabin in the woods, if you will, kind of thing. That when the snow falls down and lands, okay, we're counting on the wind to remove that load. Well, the trees are providing a block to that, okay? So this would be considered as a sheltered situation. The roof is below the tree line so that when the wind comes over the top of the trees, it's sheltered. It's not pulling off all as much as it should. Okay, that's the definition of a sheltered roof, if you will. Okay, all right, so that gets us to those values. Okay, so for exposure, the table that we're looking at this table 7-2, and you can see that you have your BCD category. And again, that comes out of the wind exposures coming out of 26.7, and then the exposure of the roof. Okay, and this is going to get us our what we call our CE, our exposure factor, on there. And you can see that for the case is calibrated for a B or C partially exposed. That's the 1.0 case. But if you go to a sheltered structure, you're adding 10 or 20%. And if you're fully exposed out in the middle of an open field, you actually save 10 or 20% as a result. Okay, and then of course there are some special cases above the tree line in windswept mountain areas. It's very low because it's very windy. In Alaska, in areas where trees do not exist within a 2-mile radius of the site, you're also allowed to use the lower one as well. And there's some more reading that you can do about obstructions and distances and those kind of things and how that starts to affect. Okay, but for the sake of our discussion, just kind of the basics, that's where the values are coming from. All right, the thermal factors then are basically, is your building heated or not? Okay, and it basically defines the freeze-thaw characteristics of the structure. Okay, and it's heated versus unheated. Okay, and so it's evaluated based on interior temperature. Okay, and so you can see all structures except those indicated below is 1.0. Okay, structures kept just above freezing and others with cold ventilated roofs. So these are like your refrigeration buildings and stuff. You're going to gain a 10%. Okay, unheated and open air structures 1.2. This would be like your ag barns, and those kind of structures. Pavilions, on campgrounds would fall into that category. Structures intentionally kept below freezing, again, kind of if you're intentionally keeping it, you're going to pay a penalty. It's 30%, 1.3. And then continuously heated greenhouses, with a roof having a thermal resistance less than 2 degrees Fahrenheit times H times the feet squared per BTU rating is 0.85. Now, a lot of times I'm hesitant to take advantage of this one. All right, and part of that reason is because what happens if the power goes out? Well, then your heat source goes away, and now you've got a problem. And in the middle of winter, power tends to flicker. So I would be hesitant on using this. And most of the time, if I'm doing this guy, I would go up into a 1.0 anyway. I hate to reduce it any further. But again, whatever lets you sleep at night, whatever you're comfortable with, you're allowed to reduce it. But this would, to me, would have to have some sort of battery backup or some system that guarantees that it's always heated. So that's why we have those. But those are your thermal factors, your CT values. Okay. All right. There is a minimum roof snow load. Okay, and this is only for roofs with theta less than 10 degrees. This has to be considered in addition to the flat roof snow calculations, and as well as the wind effects, which include drifting and sliding, which again, we're not talking about drifting and sliding in this video. But that requirement, this minimum requirement, comes out of 7.3.4, and here's the excerpt for that, okay? So where the PG is 20 pounds per square foot or less, the minimum snow load is taken as the importance factor for snow multiplied by PG. Okay, and where PG exceeds 20 pounds per foot squared, okay, it's 20 times the importance factor. Okay, so that's the minimum. So for those higher snow load regions, this guy will never control. It'll be this one that will start to, it will be the snow as you calculated, the minimum. But for smaller areas, things like, this would be a minimum that we have associated with, you can get some very light loads down in some of the other parts of the world. At least in the United States. If you're in some other part of the world, Europe, Asia, or what have you, then obviously you'll have to find your local methodology. You'll have to find your local wind maps to be able to accommodate that. But I think the methodology will be very similar to this. Okay, now, here are the calculations. For a flat roof snow load, when we don't have any drifting being considered, the pressure due to snow, and this F indicates that it's a flat roof, okay, it's going to be 0.7 times CE times CT times the importance factor times PG. So these are all those factors that I just described to you, okay? CE was the exposure, CT was the thermal. We showed you those on the last page. IS, this is that environmental I that came out of that table back in chapter 1. Okay, again, if you have questions on these values, go take a look at that environmental video, and we'll help explain that to you. The PG then is the map load that we have, okay, and that's coming out of 7.3. Okay, so we've talked about all of these values. For Southwest Indiana, which is where we happen to be, okay, we're kind of on the line between 15 and 20, so normally I round up, you know, because if you look back at the maps, you know, here's a 15, here's a 20. It doesn't mean that it just all of a sudden miraculously jumps 5 pounds per square foot at that location. There's kind of this blended nebulous region where it kind of gradually increases. And again, we're looking at average values. So that's why if I'm sitting on a, you know, if I'm building something that's on a line or near a line, I generally take the higher one as my number. And that would be, you know, the same for anywhere down here or even up here, that I tend to take the higher of the two values if I'm close to one of these contour lines, as we start to kind of look for that. All right. Okay. All right. Then the only other factor we have to talk about then is for sloped roofs. Okay. And so for a sloped roof, all you're doing is you're taking the PF value that we just calculated, that flat roof snow load. And again, when I do this computation, the units on this are PSF and everything else is unitless. So I'm doing a PSF calculation. Okay, for a sloped roof, all I do is I come up with a new factor for CS. Okay, and then that gets multiplied by the PF. Okay, and these are taken from a couple of charts, 7.2a, B, and C, and will depend on the heating of the building and some relative roughness of the roof with regards to sliding. Okay, and I'll point out on that picture, I'll go show you that slope factor, that for most structures, typically the solid line is going to be used. But here's what the picture kind of looks like. And if I pull this out a little bit, okay, there are basically three charts that show up on this. The first one is, it says warm roofs with CT less than or equal to 1.0, cold roofs with CT equal to 1.1, and then a cold roof with CT equal greater than 1.2. So you choose your CT factor, and that dictates which chart that you go into. Okay, and all we're looking at then is to get our CS value, there are these series of lines. Okay, and so we're most often playing with the solid line. Okay, and so again, this has to do with the roughness of your structure. You know, is it some sort of corrugated system or some sort of very smooth metal roof system where things will just slide off in sheets? You might be more toward the dotted line, but for asphalt shingles on a house, I'm pretty solid using the solid line here. So all you do to get the CS factor is basically you take your roof slope, okay, so and it goes from 0 to 90, okay, and so, you know, 45 is here, 4 on 12 is down about here or something, you know, and you can see we've actually got, you know, 3 on 12, 4 on 12, the actual slopes expressed that way, that, you know, a 4 on 12 line would be here, so my CS factor is, you know, 1.0, that there's going to be no minimal. But if you start thinking about, you know, your ski chalet in the Alps or something that has, you know, a 70-degree roof, well, the reason they did that is because 70 degrees is here. Look at the difference. It goes from 1.0, basically that 70-degree roof guarantees all the snow will fall off, and my structure doesn't have to hold it. So most structures are in between. They're somewhere on this line, and that's how you read this value. So all I do is I read up. So let's just say we took a 40, 50. Let's take a 45 degree. We come up to here and then come across. You can see my CS is basically around 0.5. You'd have to be a little more accurate than I was, but that's how these charts work. So once you calculate the flat roof snow load, that's how you get CS. Figure out which chart you're in and then pull the CS off of it, and away you go. And you can see they're all a little bit different based on, but they're all work the same way. CS on the vertical axis and the angle of the roof on the other, and then the roughness lines that you have, you know, unobstructed slippery roofs, and then all other structures are here. So anyway, hopefully that makes a little bit of sense for you. Okay, so that's that part of it. Okay, we do have, let's see, let me go back. There is one other issue that occurs with snow, and that has to be with what we call unbalanced snow loads. Okay, now this is a little bit different than drifting, but at the same time is a little bit similar. And so what happens is that on roofs, because that's where snow occurs, we don't load the walls with snow, but on the roof, okay, the first case that happens is case one. It's just a balanced load. We're going to use our PS value, and it's applied uniformly over the entire roof area. Okay, and so this is our distance W. It's from the windward wall to the ridge. Okay, and so I would have a constant pressure of PS all over it. Okay, now imagine that all the snow is laying on the building and then the wind hits and it blows and it blows and it blows and it blows. Okay, it's possible for me to have a case then whereby the wind, when W is less than 20 feet with a roof rafter system, that all the snow on this front slope from here over basically gets redeposited over on the back side. Okay, and so if that's the case, then I have what we call an unbalanced load. But this is a design case that you'd have to consider, okay, because this can load your structure in a slightly different methodology. Okay, and so all we're doing here then is the load back here is we're putting a minimum I times PG on this guy. Now again, this is only unbalanced for W less than 20. Okay, now what happens if I have this case and then the wind flips direction and is now blowing in from this way? Well, I can get a little bit of a redeposit, and you can it can build up, and the ridge will catch a little bit. And so this is the start of talking about some of these complex drifting mechanisms, that occur on the roofs. There are more as well, but just kind of giving you a sense of there are 3 cases for the unbalanced roof that you have to be able to sketch and to consider. But once you get the sketches, then you're playing the exact same game. All of these units are PSF, and you can now take those and start to distribute those out to the members that are supporting them and do your structural analysis or your modeling based off of that. All right, so the unbalanced other case then, is if W is greater than 20, I get a case that looks like this, whereby the wind kind of piles up, and you can see the dimensions. Here's the PS value that we had. This HD is actually a drift height calculation. Again, we're not talking a whole lot about that, but there is a more complex one that shows up when we have a large building. Most houses will fall into this category, but if you get into bigger commercial buildings or sawtooth roofs or something, you can get into this one as well. Again, we're not going to deal a whole lot with that, but I want you aware that it's there and that it's happening. Okay, for theta is greater than 30 degrees or less than 2.38 degrees on here, this unbalanced load cases don't need to be considered. Okay, all right. So with that, I think we will call it a day. We'll pick up on drifting on the next time. All right. So anyway, kind of walk you through our packet method. Okay, is maybe you have a structure, a gable roof apartment, and we're trying to figure out what the snow loads are that are acting on this roof. Again, the way that this works out is you have to know the type of structure, you have to know the location. Of course, you need to know the roof geometry. So this roof has 30 degrees. Okay. And then some site info, which mentions, several small trees in the area, but no significant clustering of conifers. Now, a conifer is basically a tree without leaves. It's like an evergreen or a pine or something like that. And that's important because if you have conifers in the area, they don't drop their leaves in the winter. Okay, if you're sitting around near, a maple tree or an oak tree in the winter, they drop their leaves, and it's, the exposure of this building being surrounded by those is completely different than if you have a pine tree that's sheltering things. Okay. So just like we did with the wind cases, you basically go through and get your structural data. We figure out our exposure, is the roof sheltered, partially exposed, or exposed, what building category, what importance. So these are those environmental factors again, and then I've added the roof sheltering also as a factor for you to determine, well, which one is it? Okay, and part of that has to be, you got to look at, well, how tall are the trees around you? Well, your building is, your mean roof height looks to be around 140 and your base is at 100, so your building height is 40 feet. Are these trees more than 40 feet tall? I don't know. You have to kind of look at the site. Now, again, with trees, I'm a little nervous to take those into account when it comes to wind because somebody can always cut the trees down. Okay, well, in snow, you want to consider the opposite case, is that 50 years from now when those trees grow up, will they change your shelter exposure on the building? Will you go from partially exposed to sheltered? Well, that changes. So a lot of times, I'm taking the worst of the assumptions as I start to try to figure out what those values are. Okay, and then once you do that, you've got all your structural data and your environmental data. Now we can come in and we can actually do the computations. And just like you did before, you're going to find CE, CT, IS, and PG. Okay, you're going to compute the minimum roof load. That's the minimum value. And then you're going to calculate PF, and then you can take into account the CS scenario that looks something like that. Okay, and then the final exercise for this assignment then would be, we have unbalanced parameters. We're not going to be dealing with HD or gamma or anything because that was drifting, so we won't be doing that. But you can actually draw those 3 cases for how the roof load the snow is distributed to the roof of the structure on here. And that's basically the exercise that I want you guys to try. We'll talk more about the unbalanced parameters in a later video. when we do drifting and talk about some more complex features of snow. But anyway, I hope that that's made sense. It's a fairly short lesson, I guess. Very similar to the way that we do wind analysis. It's just a different set of factors and a different set of maps, and then understanding what the load looks like when it's put onto the roof of the structure. So I hope that that's made some sense to you. So if you got any questions, again, toss me a comment down below. I'll be happy to help you out. Otherwise, you guys have a wonderful afternoon, and we'll see you guys next time.